Hello, my name is Randila Beiratna and this is my final project analysis for Decision Science 725. So, telemarketing is a very popular strategy used by many companies to promote their products and services. Usually, they call around thousands of customers. Therefore, it is very crucial to identify the customers that will agree to telemarketers offering. So what is our goal here? We use some marketing campaign data and then we are going to build some statistical models to predict whether the customer will subscribe to a certain term deposit or not. So this data was actually a telemarketing campaign data conducted by the Central Bank of Portuguese Republic. So the purpose of this project is to reduce the cost through an effective. So what is this effective telemarketing? So calling thousands of customers is very expensive, but if you know the correct customers to call, then you can do that task with less number of employees, with lesser time. Bank can use this saved extra time or money on some other projects. Now let's go through our data. So the dataset has acquired from the machine learning repository in UCI. This is a classification problem because our response variable consists yes and no depending on the customer's responses of whether they will subscribe to a service that provided by the bank. This dataset contains more than 4,500 observations and 17 variables. So the dataset was already clean, but we performed some data cleaning methods anyways. So first we checked the null values. We didn't find any. Then we checked outliers. We found some outliers, but we didn't find any significant outliers. So, but I did one thing that I changed the data type of the predictor day. That means day means 1, 2, 3 to 31. So that day was in numerical. So we don't do any calculation on a variable like day. So I changed that to numerical to categorical. So except for that, we didn't do any transformation. So we divided the data set into two sets, training and testing set. The training set contains 80% of the data observation and the test set contains 20% of the observation. So in the total data set, roughly 89.86 of data has no value. So that means there is a class imbalance in our data. So I will explain later how I overcome that. So the goal here is to find the best model for predicting customer responses. High accuracy is not the only result that we are expecting. Telemarketers need the set of customers that will agree to subscribe to their service. That means we need the set of customers whose response value is yes. Therefore, we are calculating the sensitivity in order to identify how well the model is predicting the true positive values. Likewise, it is good if we can minimize the false positive values too. So we calculate the 1 minus specificity also. And we used R 3.4.0 to create our predictive models. Let's go through the naive method. In the test dataset, there are 937 observations. Let's just say that our result contains the value no in all the 937 observations. If we compare that set with our test dataset, then the accuracy of this model would be 88.79. So we can see that we need to build a model that can generate a higher accuracy than this one. Actually, I started using the LVQ model as a feature selection. Then I figured out that I can use LVQ as a method in K4 cross validation to train my data. So I went for it. LVQ model makes predictions similar to the K nearest neighbors. Predictions are made from searching all vectors for the K most similar instances. After that, the model summarizes the output variable for that K instances. Now, how does this model find the final prediction? Actually, it uses Euclidean distance. After that, I calculated the feature importance and came up with this graph. So you can see the duration has the highest importance. So this makes sense. Longer the customer talks, more interest the customer is. Yes, then we did like 8 different iterations. So first of all, we tried with all the predictors, then 12 most significant predictors, and then 8 most significant predictors. Then what we did was we kept our model to 12 most significant predictors and changed the number of false and number of repeats. So we can see that the model number 5 is give us a pretty good performance like 89.75 and sensitivity is 20. So but then what we did was, so currently the no to yes ratio is 88 to 12. So this is clearly a class imbalance, like I said earlier. So therefore, I use an oversampling method to bring that data set for a 50-50 yes to no ratio. So with the oversampled dataset, we got this coefficient matrix, and we got the accuracy around 64, sensitivity around 61, and false positive rate around 35. So you can see the accuracy has dropped, but the sensitivity and the false positive rate has increased. So as you can see here, the model without the oversample data and model with the oversample data, you can see that there is a big difference. So that means, I mean, you can see the class imbalance has a big impact here. Okay, the random forest is the next model I tried. So the random forest has the ability to avoid overfitting, and it can deal with a pretty large number of features. So the random forest considered a random sample of predictors as split candidate for the full set of predictors. So this split is allowed to use only one of those predictors. So there are two parameters in random forest. First one is entry, and that is the number of trees that random forest make, and the second one is mtry. That's the number of random sample predictors used at each split. So random forest works in 3 steps. First step, it creates the bootstrap samples for the given value in the entry. So for each bootstrap sample, it grows the unpruned tree by choosing the best split from the mtree, and after that the model predicts the new data using the majority vote. So first we did the feature importance, and as you can see it's the same as the LBQ model with little difference. So yes, we did 10 iterations. So first 5 iterations with all the predictors and the last 5 iterations with 12 most significant variables. So we change our entry values, we change our entry values, and I came up with a model iteration 5. You can see that it has a 90% accuracy and a 50% sensitivity. So in overall, this iteration 5 is pretty good. So after that, we did oversampling to random forest too, but as you can see here, the overall results are not good as previous. So there's no significant difference between the model with oversampling and model without oversampling. The third one is k-fold cross-validation. So the k-fold cross-validation is a resampling method. So it randomly divides the set of the observation into k groups or folds of approximately equal size. So let's just say you have a 10-fold. So you divide your dataset into 10 groups. So the group number 1 you consider as the test fault in the first iteration, then the other groups are the training fault. So the iteration number 2, you consider the group number 2 as the test fault and the other segments as the training fault. So you do that, like if it is k fold, you do that k times. If it's tenfold, you do that 10 times. So the performance is calculated by the lowest MSE, that means mean square error. So the k-fold cross-validation estimate is computed by averaging that MSE of each estimate. So we used this model as a LVQ method earlier. Now we are going to use the random forest method. So k-fold cross-validation has two methods in its training control. One is cross-validation, one is bootstrap. So we tried both of these and we came up with these results in sixth iteration, but we had better results with earlier models. And we did oversampling with k-fold cross-validation and the results are same. It's not good enough. And here you can see the results are same with or without oversampling. So last but not least, we tried classification. So classification tree predicts that each observation belongs to the most commonly occurring class of training observation in the region to which it belongs. So when interpreting the results of the classification tree, we consider the class prediction in a node as well as the class prediction among the training observation that falls under that region. So in this model, we use recursive binary splitting to draw a classification tree. We can get the model's error from classification error rate, which is the fraction of the training observation in that region that do not belong to the most common class. So when training the data, there are two types of splits I use. One is deviant split, other one is gene split. So this is the performance of first two iteration with both of that splits. Well, it's not good, and why it's not good? Because it was unpruned. So what I did was I then pruned the data to reduce the complexity of the tree, and then it helps me to reduce overfitting. So yes, first start with the deviant split. So we perform a cross validation in order to identify the optimal tree level of tree complexity. So you can see here the tree with terminal node 5 has the least cross validation error. So this is the tree with the least cross validation error. Then we did it with gene split. So with gene split we got this graph, and according to this graph you can see the terminal node 3 has the least cross validation error. But we tried with 3, 9, 16, 41 and 71 to see what's happened. So we got some pretty good results with classification tree. So as you can see here, the gene split is better than the deviant split, and the iteration 4 and iteration 8 showed us some higher accuracy values and higher sensitivity values. And after that, yes, oversampling. So after using the cross-validation on our dataset, we found out that trees with 27 to 34 terminal nodes have the lowest deviance. So therefore, we ran 3 iterations by pruning the tree with 27, 31 and 34 terminal nodes. So, and after we ran the model, yes, of course. So we got the best model we have ever encountered so far. So if you can look at the terminal node 27, the model with the terminal node 27. So you can see that it has a very high sensitivity. So nearly 3 out of every 4 yeses have been identified with this model. Sensitivity matrix. So yes, so the this is the iteration 4 with the high accuracy, and this is the iteration 8 with the highest sensitivity, and the last one is the oversampled with the 27 terminal nodes. So you can see that the sensitivity has increased while the accuracy has decreased. So it's kind of a trade-off. So the final summary, let's see. So the first thing we did to overcome overfitting is choosing a large dataset. Our dataset had more than 4,000 observations, which is considerably a large dataset. So the second thing we did was choosing the most significant predictors. This way we reduce the architectural complexity, and that help to reduce overfitting. For each model we perform several iterations by changing the tuning parameters in models. This has helped us to tune model in order to perform very effectively, and having several iterations was helpful to identify the most accurate model. And yes, if you do remember, we use K4 validation, which is sampling method, and to address the class imbalance, we use oversampling to generate a dataset with 50-50 yes to no ratio. So, so this is all our models. So I use the best iteration without oversampling and the best iteration with oversampling in each model. And as you can see, the accuracy hasn't increased more than 90%. So, I mean, our naive value also had somewhere 88 point somewhere like that. So we went for the specificity value. You can see the LVQ model with oversampling and the classification with oversampling has a pretty good um, sensitivity value. And if you want to do both accuracy and sensitivity, the random forest is has 90% accuracy with a 50% sensitivity. So what is our conclusion here? Actually, we couldn't create a model with an accuracy higher than 91%, but two model accuracy actually matter in this case. No, actually what matters is higher sensitivity. So highest sensitivity we achieved is the 71.43% from the classification tree. So what I recommend is the classification tree model with 727 terminal nodes that trained with the oversampled training dataset. And thank you for listening.